Welcome back to ECE 441A, 541A. Hopefully that red doesn't alarm you too much, but our exam number 3 is on Friday. Homework number 7 is due today, and Lab 3 and the project, which is a 541A project, those are due at the end of the first week of December. But the Lab number 3 material you need to understand going into exam number 3 because I'm assuming you can design PID-based controllers on exam number 3, and that's a part of lab number 3. Lab number 3 is also dealing with phase lead controllers, and you'll want to look on D2L at the practice. The format of exam number 3 is a little different than the first two. There's more problems. They're maybe not quite as long. The number of problems has increased, and it's really so that I can test you on the different rules or the different strategies that you need to know in creating a root locus or designing with a root locus. The process, so our goals for today are to quickly go over the process, and then we'll start playing this game of stabilizing unstable systems. We haven't really been dealing yet with an unstable system too much, and let's see what we can do with the knowledge that we possess in terms of where do we place poles and zeros if we need to stabilize an unstable system. The process for exam 3 should be consistent with what we've had so far this semester. We've just added another page to your sheets of notes that you are allowed, and those sheets can be both filled up on the front and the back. You can bring a photocopy of a Laplace transform table from page 59. You can bring a calculator. You can bring all of your drafting tools if you want, your protractor, your divider or dividers, and a ruler, and that will be in. The idea is to help you with your sketches. You might want a straight edge, even if it's not a ruler. You might want a straight edge so that you can quickly draw some lines that might be helpful in sketching these root locus diagrams. Obviously, you need something to write with, but then there are several no's to be attentive to, and I guess I didn't put no neighbor, but you won't be allowed to access your neighbor on the exam either. But no cell phone, no computer, no class notes, and no book. Let's get into then stabilizing unstable controllers, and this will be on the exam. You will need to know this kind of technique or these strategies, and most of the time we will play with a traditional block diagram where we may not have anything in the feedback path. We have unity feedback, but it's typically or traditionally negative sign, but maybe at the end of today we will talk about what happens when we change that feedback path to a positive feedback. That changes things in terms of our root locus rules. But right now, if no one tells you otherwise, this would be the traditional block diagram that you would be using or thinking about in designing controllers. So that shouldn't be a surprise, and actually that diagram should be just front and center in your mind or head, and maybe you should just always look at that before you go to sleep at night. And then you have it right there, and you know what the transfer function t is for that particular system. Here's question 1 for you to answer. Suppose that the G, the plant, in that block diagram is 6 s minus 1 factor over 2 factors, an s and an s plus 2. Can that system be stabilized in this traditional negative feedback configuration with a positive gain k? Can you stabilize that system? take a minute, and that's all it should take you based on what you know at this point in the semester. And on Friday, for the exam, you'll want that to take you a minute or less. That's the speed with which you need to be doing these kinds of problems. Can you stabilize that system with a positive K? And depending on your answer, you need to justify that answer. The answer is an up or down, yes or no. That one's easy. So you could take out a coin and flip it, and then you would maybe have reasonable odds, better than Vegas odds. You could win half the time. What did we decide with our thumbs? I'll just get the yes or no, and then we'll see if we're in agreement. So thumb up if it's yes, thumb down if it's no at the count of 3. Is everybody ready to vote? 1, 2, 3. So most of you were leaning negatively on this, and why is it a negative decision as far as can this system be stabilized with a positive gain K? Why can it not be stabilized? And I would say the justification could be a straightforward root locus sketch. You have this S-plane, and in, I hope, very little time, you could say, oh, I have a 0 there, I have a pole at the origin, and I have a pole at -2. That should be boom, boom, boom for Friday. Then you should quickly use one of your first rules, and you don't have to know the number of these rules, but now I'm looking for you to chop up the bread and to determine which pieces of that real axis belong on the root locus. In this case, we have a segment between the origin and +1, and we have another segment to the left of -2. And no matter how we adjust that gain K from 0 positive, that poor pole at the origin is going to be stuck in the right half plane. The justification then would be the root locus implies no, we cannot stabilize that system with a positive gain K. Is that clear? That particular closed loop pole is stuck with a positive real part. If you simply, in our traditional feedback configuration with negative unity feedback, G sub C being a positive gain and G being this particular pattern of poles and zeros. Now we have a 0 in the right half plane. That's a non-minimum phase system. We'll talk more about that maybe when we get into Bode plots. That's not important, but the important piece today and Friday is that you can't stabilize that with a positive gain. And I keep emphasizing positive gain because we can change things up a lot if we actually used a negative gain. But we haven't been dealing with that. Let's ask another question with that same system. Question 2. Is it possible to stabilize that with a first order controller? Is it possible to stabilize the plant G of S? It's the same plant, but I'll go ahead and write it again. 6 S minus 1 over S, S plus 2. with G sub C of S being K S plus Z over S plus P. Is it possible to stabilize that system with a first order controller? That's now what when I say a first order controller, you should just immediately think that structure for G sub C. Take a minute to figure that one out. Again, it should take you, and especially after we've done this a time or two, it will take you less than a minute is the intent. Can you stabilize that system with a first order controller? And you can talk it over with your neighbor. Convince your neighbor that you're correct, your design. Yes or no? Was it a? Can you stabilize this system? 1, 2, 3. Thumbs up or down? So we're a little bit mixed on this one, and this one is a little bit more challenging because we haven't really talked too much about it. We haven't changed the open loop system. We still have a pole or a 0 in the right half plane. We have a pole at the origin, and we have a pole at -2. And with a gain controller, a positive gain controller, we can't do that, can we? We can't stabilize it. We need to somehow get some of the branches at all the time, or all, how do I want to say this? All the closed loop poles at some point need to be in the left half plane in order to stabilize it. That doesn't mean that the root locus always has to live in the left half plane. What's the thought process here? Somehow we need to eliminate this branch, don't we, of the root locus. We need to get rid of that. We need to somehow not even let it start or be there. Because if it's there, that pole at the origin is always going to be stuck. We have to somehow, so the thought process is to eliminate the root locus branch for just a pure gain controller that occurs between the origin s equals 0 and s equal +1. And how are we going to do that? Now you have to maybe think a little bit outside the box, but what would happen if what do we try, or how do these branches live on the real axis in the first place? When there's an odd number of poles and zeros to the right. So now, can we somehow put something in the right half plane to allow this piece or this segment of the real axis to no longer be present? So now if we put a 0 over here, either there, somewhere in the right half plane, we could put it there, but we need to put a 0 over there, don't we? So the idea, or how we're going to do this, is we are going to place a 0 in the right half plane. The idea here is we are wanting to change, or the fact that we put a 0 over there in our controller, let's just put it right there. Let's say it +2. Is that where I put it? Who knows? So now let's put a 0 there, and that changes the root locus segments on the real axis. Now what do we have in terms, and can we just put a 0 down by itself? No, we can't just add zeros. It'd sure be nice if we could just get out our zero shaker and sprinkle zeros all over, but then we would have these derivative actions. And remember what a derivative Bode plot looks like. That just keeps going up and up as we get higher and higher frequencies. And so if we have any noise, that noise is amplified a lot by these derivative actions. We need to then roll that off with a pole. So we can't just arbitrarily be shaking zeros all over the place. We have to pair those up with a pole. There was a question in the back is, now can you just put a pole at infinity? Yes, you can, but you have to build this. So go tell your boss you need to put a pole at infinity, and they're going to say, well, we can't even communicate with things on that asteroid. So infinity is yes, that's the right thinking. And what you would say then is, well, what is infinity? And it's sort of like this infinity of time. It may not have to be that far into the left half plane. Like our 5 time constants is like infinity. Let's say that we put a pole right here at -4. So, whoops, let me change the color of that pole so that we can, because all these poles are not all from the same cloth, are they? The red poles and zeros are the plant. The blue poles and zeros are the controller, just to sort of let you know what's being sprinkled where. If this is now the pattern, we now have matched a 0 and a pole. We definitely don't want to make our infinity go to the right, do we? We didn't want that pole to positive infinity. Then it would just be flying into that 0 at +2, and it would always be unstable. Our infinity, in this case, I'm assuming you were thinking, is minus infinity. It's not plus j infinity or minus j infinity. Those have to occur in conjugate pairs if we're going to build this with a real system. So we located it at -4. Now which pieces of the real axis belong to the root locus? Between 1 and 2, is that on the root locus? Between 0 and +1, I forgot +2 and infinity, but I'm assuming you know that's not on there. What about between 0 and -2? -4 and minus infinity. And that could be a question on the exam. Boom, you're done with one question. Move on. It might just say identify the real axis segments, so shade them nice and bring an eraser. I forgot to say that in the process, but usually you don't want to erase. Just draw another diagram and say forget that one. It's quicker. Plus it's not as messy. Now what's the root locus look like? Are we done with the root locus though? If we had to sketch a complete root locus, are we finished? How many closed loop poles do we have? Are we counting down? 4, 3, 2, 1, and hoping we reach a number. Closed loop. How many closed loop poles? 3. We had 3 open loop. We're going to have 3 closed loop. So we have 3 branches of the root locus. And that's not consistent with these lines. We have 3 real axis line segments, but those actually, this line segment is really 2 branches of the root locus. This line segment possesses 2 branches of the root locus. Because we start at poles, this one is going right, this one is going left, and they can't just stay and have a party in the middle, can they? Once they meet, what happens? They break away. So there's a breakaway between the origin and -2. What about out here in the right half plane? Now we've really cranked up our gain. A closed loop pole will approach that finite zero, and another closed loop pole will approach that finite zero. There's a re-entry there. So those arrowheads are telling me where 2 of my branches are. I have 2 starting in the left half plane, and I have a 3rd branch right here. He's just in isolation. He just keeps going off to minus infinity. But now I said that we have to break away, or you guys told me, so we break away, and we're somehow attracted over here. And if we were just doing this quickly on a test, we may not want to find the breakaway and the reentry points specifically, but given time, you should be able to do that. What's happening at a breakaway point? You're looking for a relative maximum of the gain, aren't you? So if you iterated, or if you did the differentiation, you would find that the derivative of k between 0, the origin, and -2 would reach a relative maximum for some value of s between 0 and -2. Can we stabilize this system? So what have I done? I've actually, now we're starting with k small, and what I have to make sure is that I don't crank up k too much to get me into the right half plane. But if I keep k small enough, I can have a stable system. What's the location where I would start to become unstable? The branches will eventually get up to those imaginary axis crossing, and if I crank my gain up, and you could calculate if you knew this, how would you verify if that top square was on the root locus? How would you verify that on the exam on Friday? How would you convince me that that upper square is on the root locus? I would say, prove it. And what would you do? Pull your hair out? Mine's already out, mostly. There's 2 conditions, aren't there? When you're studying for this exam, there's the magnitude condition and the phase condition. Which one would you use to convince me that the root locus is at that point on the imaginary axis, or not? You would be given that point. So if you're given that point, let's say, and you could find it, couldn't you? You could find it with the root array. You could find it algebraically. You could find it by using the phase condition. You now would check and say, are the angles, and which angles would you be checking? How many angles would you have to find with your protractor or compute with your calculator? How many angles? All right, now I want to see fingers. the count of 3, show me how many fingers, and I think we have enough fingers because you have 2 hands. 1, 2, 3. I see a lot of high fives, which is correct. We have, I think, let me look. We have 2 zeros. We have an angle from each of those, and we have 3 poles. And we would compute the angle from each of those to the rectangular box. Is that clear? The angle from +2 to that point would be what? 140 degrees, just eyeballing. The angle from +1 to that point is less than that, maybe 120 degrees. And this you could quickly do if you sketched it somewhat accurately. You could measure those fairly quickly with a protractor. Then from the pole at the origin, that one's easy. That's 90 degrees. And you're subtracting now all of these pole angles. Then the pole at -2, that looks like it's less than 45, the way I've sketched it. And the pole at -4's angle is even smaller, isn't it? So you would add those up algebraically. Does everybody understand what I'm trying to say? You have 5 angles, you have 2 zero angles and 3 pole angles, and you would be checking to see if those angles all added up to -180 degrees. If they added up to -150, what would you say on the exam? Is this triangle or is this square on the root locus? You would say no, because it doesn't satisfy the phase angle condition. That would be your justification. Is that clear? So I'm sort of reviewing for the final. For the exam, now I've lost my pen, so maybe we're done for the day. No, we're not that, you're not that lucky. I don't want to lose this because I want to keep talking. Question? So now the question is it legal to put a 0 at the origin? So now you're modifying my controller design. Is that true? You're saying, is it possible, is it legal? And now, do we have any lawyers or any police officers here to talk legality? That's not my forte, but we can answer it based on some engineering. Where was I? Trying to do this legal challenge. We have a pole there, we have a 0 there, and a pole there, and the question was, can I do that? And put another pole over here. Is that right? So answer me. Why can we do that, or why can we not do that? So now the reason we can't do that is I have basically told you that you cannot cancel poles and zeros on the imaginary axis or in the right half plane. Given time will show that there could be a transfer function between a disturbance and the output, the reference and the output. One of those transfer functions will give us a pole at the origin. And then if somebody gives you a kick or a constant, that's going to cause your signals in your system to go unbounded because it has a pole, a fixed pole at the origin. So that's a no-no. This is a no, 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 no. Okay? As far as this guy. Now you could say, oh, I like that idea. Oh, if I could just do it. Well, this isn't a Nike commercial, but you can. Sorry. You guys, stay with me. You could do that. That's okay. You're just not canceling that pole. but you kind of like that idea. You kind of liked it being there. Now you just have it maybe at 1/2 or 1/4, and now you have, well, you would still have another pole there, but you have the same general shape that we had before. And those are supposed to re-enter at the same point, even though I didn't sketch them properly. What was I trying to do now? Oh, so now I like this pattern. So now I'm going to say this is my controller. How do I finish up the design? I now have a controller, G sub C of S is K, S, where did I put that one? At 2, and this was S plus 4. That was my OK controller. Now, I'm not done, am I? I have to find K. How do I find K? The magnitude condition. And what would be a quick way? You now have 1 minute left on the exam, and you go, oh, I need to find K. I put my pole and 0 down. A quick way to do it would be to say, well, I know that for small values of gain K, I'm going to have 2 poles between 0 and -2. Why don't I just pick a spot between there? The other one's going to be to the left or the right of that point, but it'll be in that region also. And the other one will be off to the left of -4. What I'm saying is I would just say, oh, why don't I pick a pole at -1, and then another pole would, let's say, if the breakaway is correctly drawn, which it may not be, I would have another pole approaching that breakaway, and then I would have my third pole over there. Meaning, to find this gain K, use the magnitude condition. So that now I have G sub C, G equaling 1. Or for the numbers that we have, I have K, S minus 2 over S plus 4. That was my controller. My plant was 6, S minus 1 over S, S plus 2. And I need that to equal 1 to satisfy my magnitude condition. I can now solve that for K, and I have the magnitude of S, the magnitude of S plus 2, the magnitude of S plus 4, all divided by 6, S minus 1, S minus 2. And I said, oh, let's look at one of the closed loop poles being at -1. So let me evaluate that for a gain of, to get me to a point S equal to -1. And now this is pretty quick. You could do this in a minute. The magnitude of -1. 1. The magnitude of -1 plus 2. See, this higher level math, you really have to make sure we're paying attention. That's also 1, isn't it? -1 plus 4 is 3. I now have that 6. That was given to me as a gain in the plant to begin with. The distance, what I'm doing is I'm just saying, oh, I have a closed loop pole there. I now need to know the distance from this point to that point. 1, 2. So the distance, or the length, of this factor is simply 2, and the length of this factor, whoops, is now 3, right? This one is there, and this one is there. And that's not too hard to compute. K of 1/12 is what I want. So I'm not cranking up my gain very high, and I'm getting one of those poles to -1. But now I have my controller. My controller, G sub C, is now 1/12 S minus 2 over S plus 4. And that will stabilize my system that with just a pure gain was not capable of being stabilized if the gain was positive. Are there questions on that controller design? Let's play some more. This is kind of fun. Let's do question 3. Let's change up our system. Now let's say we have a plant, G of S, that's 5S over S minus 2, S plus 2. Can that plant be stabilized with G sub C of S equaling K, where K is again positive? And you need to justify that answer. Again, you have now 30 seconds, because you should be able to do this in that amount of time on the exam on Friday. All right, our 30 seconds are up. Is it stabilizable with a positive gain K in our traditional feedback structure? I see quite a few heads going left to right, which means no, I believe, in the United States. We now have a 0 there, a pole at +2, and a pole at -2. And if we just sketch the root locus for this, now this pole is approaching that 0 from the right, and this pole is going off to the left. And that's all there is to that root locus, isn't there? What's the pole 0 excess? 1. How many asymptotes do I have? 1. What's the angle of that asymptote? -180. See how quickly you can start answering a lot of different questions? All right, now let's do question 4. Let's stabilize this with a first order controller. So question 4 is find G sub C of S equaling K S plus Z over S plus P to stabilize G of S in question 3. Need more time? What's our strategy here? Now we need to put a pole in the right half plane. A zero is not going to cut it, is it? A zero in the right half plane is not what we want in this case. We need to get rid of that branch of the root locus between +2 and the origin, and one way to do it is to put a pole over here in the right half plane. You could put it at +3, you could put it at 2, you could put it at +1. You know, it's going to be easier if I just do it here. It doesn't matter. But if I put it right there on top of the other one at 2, what's the root locus look like? Well, now what's going to happen for this controlled system? What's my pole zero excess now? It's 2, isn't it? That's a double pole. So I've drawn it. The question was, is that a double pole or is that off the real axis? It's both, but what I'm implying is it's actually right on top of the other pole at +2. I just wanted to emphasize that I have 2 poles there. Okay, so I have 2 poles right on top of each other at +2, and maybe what I should have done is what I was doing before, and make that blue. That's now a controller pole with the plant pole. But now that's not going to quite cut it necessarily, because what's going to happen if I had a root locus now? What parts of our bread belong to the real axis? +2 to infinity? No. +2 to the origin. Is that on the root locus? Why is it not on the root locus? Because you have an even number of poles to the right, don't you? What about from the origin to -2? Yes, that's the only branch or real line segment that's a part of the root locus for this picture. So this is not quite, we don't want to finish here. What I would do is I would say, oh, I could put a 0. Why don't I just cancel that one? Now you can effectively erase that pole 0 cancellation. And what's the root locus look like for this configuration of poles and zeros? Now what's my pole 0 excess? What's my pole 0 excess? I have 3 poles and 2 zeros, don't I? So I have a pole 0 excess of 1. How many asymptotes does that mean I have? What part of the real axis belongs to the root locus? And what's going to happen at those 2 poles in the right half plane? They're going to break away. They have to get off that real line, don't they? Because there's no piece of the root locus on that real line. These are actually, the reason I put that one at +2 is it makes my root locus sketch very easy. Now I have a pure circle. If I had my compass, forgot to include that on what you could include, you now have a radius of 2 with a pure circle. These now leave those 2 poles. One goes to the origin and one goes to -infinity as you crank up the gain k. Here, in this configuration, now you need to advance that gain k a fair amount. You can't start it close to 0 or you're going to be stuck in the right half plane and be unstable. You have to crank up that gain to be beyond a gain value that would put you here. Does everybody see that? Now you have to be beyond a certain gain value k, And if I was on an exam and I had to calculate a stabilizing controller very quick, I would say, oh, let me just pick one there, and maybe my second pole was right there. My third pole is actually right there. It's stuck because I canceled that pole. I still have 3 poles in my system, closed loop, and that one's stuck right there, so that if I now have this G sub C of S is K, S, where did I put this one? I've got so many symbols here. I put that one at -2, didn't I? I canceled the pole at -2 with my controller 0, and this was a pole introduced at +2. And my plant initially, I don't even remember what it was. It was 5 S over S minus 2 S plus 2. I would now say, oh, let me let S delta be -1, and now I can calculate my gain K. Now I use the magnitude condition. I now know that K, S plus 2, S minus 2 times 5S, S minus 2, S plus 2, all equals 1. And I can now solve that for K. I can say K is going to be S minus 2, S minus 2. I could really just calculate that once and square it, that distance, but I'm going to illustrate that I have all of those pieces. Then I have a 5S, S plus 2. So I could really not worry about that. I don't really have to calculate that. It's just going to cancel. And then I look at evaluating that at -1. And that's pretty easy to do. I now need to know the length from the pole at 2 plus 2 to -1. That's a total distance of -1 minus 2 minus 3's length is 3. I have another 3. I have a 5. And then I have the magnitude of -1, which is 1. I now have a gain of 9/5. And that will push me into the right half plane and back onto the real line. I'm going to have 2 real poles between the origin and -infinity. Meaning my controller now, G sub C of S, is 9 over 5 S plus 2 over S minus 2. Questions on that? All right, we have a little bit of time left. This is sort of like we have an infinite amount of time because our time constant is 10 seconds. Okay? So, let's do another problem. Can you stabilize G of S equaling 4 over S minus 1 S plus 2? With a positive gain. What's the root locus of this guy look like? What's my pole zero excess? 2. How many asymptotes do I have? 2. What are their angles? 90 and -90. Where's the breakaway? Halfway between those 2 poles, because I just have 2 pure poles. And they're separated by a distance of 3. They're breaking away halfway between that, 1.5 away from each pole. I'm breaking away here at -1/2. and I'm going up, is it possible to stabilize that system with a pure gain controller? What's the lower bound on the gain K to stabilize that system? Where would I find it? What's the minimum value of gain K to stabilize that system? Magnitude condition, and where would I apply it? Right here. So if I found the gain K at the origin, that's the smallest K to stabilize that system. What's the upper bound on my gain K? Infinity. I can just keep going with K if I wanted. I probably wouldn't want. But the lower bound for stability on K is now whatever the system was. That was now this S minus 1, S plus 2, all divided by 4, evaluated at 0. And that's pretty easy to compute. It's now 1/2. Did I do that right? Did I have a 4 to begin with in the numerator? So now I just have to crank up my gain beyond 1/2 and I'm stable. And you did that using root locus and not Ruth array or anything else. All right, exam on Friday. You need to be psyched for it. And look it over on D2L because there's a lot, it's a different structure. See you on Friday.